All right, we're going to get started. The next session today is going to be the Observations and Modeling Gap session. And my name is Tasha Snow. I already introduced myself.
Hi, and I'm Paul Winberry. And just real quick, Matt asked me to remind us all that if we look down on our name badge, there's a Pac-Man there. And what that's supposed to remind us to do is when we're standing in groups, is to always leave a space open so someone can join us so there are no closed groups.
So we have a number of great presentations coming up. I want to remind the audience that as we have our presenters come up, if there's a little bit of time, we may get a few quick questions in before transitioning to our next presenters, but we have a long discussion session or section at the end of the talks to be able to ask a lot more questions. So that's where those will be able to come in. And let's get started with Kirsty Tinto, who's going to be talking to us about the SCAR Rings Action Group in her presentation.
Thank you. Hi everybody, yes, I'm Kirsty Tinto and I'm speaking on behalf of the steering committee of the SCAR Rings Action Group, and they're working towards facilitating airborne geophysical surveys and coordinated research on the Antarctic ice sheet margin. So if the theme of this session is the gaps, this is a group who's trying to define those and build some collaboration to fill them, and you'll learn more about it in the next 10 minutes. So this is a diagram of systems that I imagine you are familiar with. The coast of Antarctica is really important. It's got loads of processes that are acting to really control what the mass loss across the grounding line and into the global sea level is for the near future. And we want to understand those processes, and we don't have all the information that we need to do it. So part of what this group has been doing is figuring out where we can most impactfully get new information and answer some of these questions. There was analysis done by some of the group members who were just comparing these different ice discharge estimates of the input-output method, and they used different bed topographies. And so this is the significance of different interpretations of bed topography for the present day ice mass balance. And it's pretty significant. That was for motivation, and this is what a SCAR action group actually is, because not everybody in the room is going to know that. SCAR is the Scientific Committee on Antarctic Research. It's an international organization that brings together Antarctic researchers. And what it's particularly good at is, and what it's based on, is building these grassroots collaborations of scientists with shared interests. So it is not giving out money, but it is providing a forum for people to have exchanges of ideas across national programs, across different regions of Antarctica. Their action groups are sort of short burn time collaborations of people. They have 4-year repeats. They can be renewed, but they have specific goals to accomplish in those 4 years. And some of the people in this room did get together as part of the SCAR Rings Action Group in Norway in June 2022 and figured out what the goals for the next 4 years would be. And those were really bullet point 3 captures most of it, to coordinate between surveys that are going to happen. So sometimes national programs are going to expeditions that are going out, and they need to know where each other are. They need to know what resources they can share, and the people who stay home and figure out what the data mean need to understand what resources they've got to rely on. So just coordinating those endeavors and making sure that people know what is happening. And we do that through the mechanism of endorsing projects, so people can ask that their project be recognized as meeting some of the defined goals of rings and meeting some of the survey targets that we identified in that workshop. as an example of what I mean by meeting some of those goals, we recognize that there's a great need for a lot more constraints around Antarctica, and we articulated those into 3 different rings that need to be observed around Antarctica. The primary one is at the grounding line, because we don't yet understand well enough the morphology of that grounding line. Then there's a landward ring that's thinking about the future grounding line, where it's going to be, what the shape will be, and what other processes are affecting the ice from the rock below it. And then a seaward ring, and I'm going to talk about primary and seaward here. And the seaward is looking at ocean heat getting into the ice. If you needed to be persuaded that we don't yet fully have a handle on the shape of Antarctica, the blue Antarctica in the bottom there is the amount of radar data that's available in BedMap 3. This is from the data release that was a couple of years ago. And then an analysis there by Julian Goddard, who shows that there's an enormous amount of that near margin, like within 100 kilometers of the grounding line, where we still don't have data points within 5 kilometers of where we're looking at. So there's a lot left to know in radar land. So one of the things that as a community we developed was this ideal grounding line. Where would you like to have this constrained, and where might be possible to accomplish? So if everybody who flies planes with radars knows where the people who need these data would like to have data, we have a better chance of being able to measure each of the different sectors and having those measurements be compatible with each other. I wanted to go to the seaward ring, partly because it's one that I'm really interested in, and partly because we're here in Florida, and Mickey's group here does a lot of great work on this. But it shows you a similar story from the gravity side of it. So where the ice is grounded, you can measure the topography with radar. Where it isn't, you've got some troubles, and airborne gravity gives you a great chance of figuring out what the seafloor under the ice is like. 4D Antarctica compiled this updated version of NGG that shows you the coverage of gravity that we have around Antarctica at the moment. Some of the gaps are clear, and some of the gaps are a little more subtle. So there's been a lot of work done. This is a summary of all the different inversions of seafloor bathymetry from gravity that's been done around Antarctica. And some of them show that you can have different answers from the same place. And I say that because it inspires us to keep working. And also, I want to reassure you with this image shows you the difference between those models from their mean. And this is the important part, that it falls well within the uncertainties that we state for this sort of model. So there is variability among these models that is interesting to me, and it's on the order of 100 meters or so, which is this uncertainty. One of the reasons that uncertainty exists, and this is very similar, well, in fact, exactly the same as the issues that we have with radar data, is that we don't have complete resolution around the whole continent, and how you interpolate between survey lines matters. So here I have some gravity highs and some different ways that they might be joined together to define a landscape. This is at a 20-kilometer line spacing. If you come into a 10-kilometer spacing, you can suddenly see the trends that start to develop. And those trends are important for the bathymetry, and they're also important for the geology, because if we can understand the trends of different features, we can understand their origins, we can understand their significance for the ice sheet, and it actually helps us to do the gravity inversions as well, because we can understand their density better. So same way as radar, when you look closely at the coverage of gravity data around Antarctica, and this is one of the most surveyed areas that we have, you still don't have better than 30% coverage of having data within 5 kilometers of where you are. So there's a lot of work to do, and a lot of work on new ways of doing inversions, new geology, and new data, which brings me back to SCAR again. So identifying those gaps was the first phase activity of the RINGS group, and now trying to coordinate the effort to fill them is the next phase. So one of the things that's happened is that projects have started to apply for endorsement. There are programs that are happening to start chipping away at the high-level observables that the action group talked about in their meeting. In order to be a RINGS project, you need to advance the science goals of RINGS. You need to adhere to the shared values document of RINGS, and we can talk about that more if we want to. But when you're trying to drum up collaboration, we need to have some common ground so that it can be a healthy and productive collaboration. So we're building that into the structure of it. The SCAR already has a data policy that we can make sure that people adhere to, and then we are able to share our survey locations to facilitate collaboration. There have been some other meetings that have been workshops tacked on to international meetings, usually associated with SCAR, and these have been geographically focused. So at the Instant SCAR meeting in Italy last September, there was a focus on what's happening in East Antarctica and what needs to happen. There was an open science meeting for SCAR in Chile this summer, and that group focused on the Antarctic Peninsula. So there we were able to get translations of the science plan into Spanish so that it's actually useful for the people who are going to be working in the Antarctic Peninsula. And there's a white paper that will come from that. There was also a workshop for the modelling group who got together at the IGS meeting in Northumbria and talked about, are the modellers being served? Are we hearing those voices well enough to be able to get the right kind of measurements? Whew. I'm about to get pushed off the stage. So if you're interested, you can join the RINGS action group if you want to. It's totally open to join. You can also get involved with US SCAR at this address. Thank you.
Thanks, Kirsty. All right, our next speaker we're going to move on to immediately. That is going to be Veronica Hegelein, who's going to be talking about the Erebus Glacier Tongue.
Sorry. Hi, my name is Veronica, and I'm a PhD student at Cornell, and today I will be presenting the results of some field work that was done at Erebus Glacier Tongue in Antarctica. So for some background, our lab has an underwater vehicle named IceFin that we use to explore these subglacial cavities beneath ice shelves in Antarctica, and soon we're going to Greenland as well. And so in November of 2018, we took IceFin to Erebus Glacier Tongue, or EGT, to serve as basically a natural laboratory in order to study these ice shelf cavity processes because it was located in McMurdo Sound, and so much more easily accessible than other spots. So at that time, IceFin was equipped with instruments that gave us data for temperatures, salinity, dissolved oxygen, pressure, ice basin, seafloor depth, and then we also had a sonar in order to measure features. But since then, IceFin's capabilities have been drastically improved. So here are each of the, here are each of the 30 dives that they are labeled A through C, with A being closest to the grounding line and C being farthest out towards the ocean, and then EGT itself is coming off of Ross Island. So just to start, here is a cross-section of each dive, and so the white in each one is the ice base, and then brown is the sea floor, and then IceFin's dive track is colored according to dissolved oxygen. So the first trend that jumps out is that the oxygen is lowest during dive A, so closest to the grounding line, and then it increases as each dive moves out farther down the glacier. And so this makes sense because as the dissolved oxygen is taken up through biological activity, it is harder to ventilate the area closer to the grounding line, and so it's harder to replenish that oxygen that is removed. However, we also see a cross-glacial trend where, especially during dives B and C, it also seems to be decreasing as you move from the southern side of the glacier where IceFin enters towards the northern side. And so the way that EGT is oriented in terms of coming off of Ross Island, that northern side is very well protected by land. And so the thought is that this also increases the difficulties in ventilation. But if you see the CCC floor here, there is a sill that runs across what is basically the center line of the glacier, and then especially during the dive B, that oceanic cavity gets very narrow, and so the sill can also work to help inhibit the circulation to that northern side. And so to further explore the influence of the sill, I divided up the cross-section into 3 regions, and so region 1 is this flat part that's kind of away from the sill. Region 2 is the area where icefield is climbing up the sill, and then finally region 3 is after icefield has passed the sill. So, having trouble advancing. Okay, there we go. So the TTS diagrams for region 1, so this one here, show that the dominant feature here is mixing between high salinity shelf water, and that's the ambient water in McMurdo Sound, and glacial melt water. And so those will mix along a linear line, and that's shown here, the black solid line, and that is mixing line 1. And this data is distributed according to depth, and so the deeper water has higher concentrations of high salinity shelf water, and then the shallower data has higher concentrations of the glacial melt water. And then if we move to regions 2 and 3, the trend changes quite a bit. And so the thought is that there is a new, slightly colder and saltier end member for high salinity shelf water on that northern side of the glacier, and that's shown with the black square here. And that is also mixing with glacial melt water. And so we only accessed that side during one dive, and Icefield was driving at pretty much a constant depth. But the thought is that if we were to get a more complete depth profile, there would be a very similar trend of this data, basically following along the dashed and dotted line. And so how we know this is that in region 3, it appears that there is a linear mixing between one specific point on the first mixing line and then another on the second. And note here that, again, Icefield is driving at a pretty constant pressure. However, we are crossing isopycnals here, and so that is indicative of diapycnal mixing, and so that means that there is probably additional energy and turbulence in the water column here. Also note that in region 2, as we are driving up the sill, we again have these lines that are clustered according to depth, but they all follow a similar slope, and so the thought is that there is a mixing between the 2 different water masses, basically across that sill. So finally, we can zoom in closer on specific features in the ice. And so I was able to calculate the melt rate at several different spots using the standard 3 equation parameterization. And all of that data pretty much fell between around 1.3 to 1.5 meters per year. And so overall, pretty moderate compared to other areas in Antarctica. And then we also see some very interesting ice features. And so the most common is these 2D symmetrical scallop-like features, and so seen quite a bit in dive B, and then also of the water column having a high Reynolds number, and so that there being turbulence driven melt. However, During dive A, as we approach the grounding line, we do end up reaching the tail end of that sill I was talking about earlier. And there, the ice features change quite a bit to what we see elsewhere. And so, for example, if we look at I-2, this is from when ice fin is still driving across the sill, and then it has not started to turn yet. And there are some crests and troughs in here that are expected to be perpendicular to the dominant flow direction, and so that indicates at this spot water is being pumped across the glacier and not along the flow as might be expected. And then finally, we start to drive across the sill itself, and so we see these here. And so these features are slightly larger, more asymmetrical, and so that indicates a lower Reynolds number. And then also note that the cavity here is only around 2 meters tall. And so the ice was very recently in contact with the seabed, and so the thought is that the seafloor itself is basically inducing some roughness onto the ice, and then the ocean is able to take advantage of that and then drive further melting. Finally here, we also see that the ice base basically looks like a tunnel, and so it is preserving its previously grounded shape along the sill as it starts to lift up. And so here we can zoom in, and then here's the actual footage. And so slightly off sill, the ice is very smooth and flat, and there's not a lot of features. And here the cavity is slightly taller. And then if we turn, we start to drive back along the sill, it'll appear here, and so that shows how close we actually are. And then you can see the slope of the ice base here and how it is basically matching the slope of the sill, and then all the more random and asymmetric features compared to what we saw elsewhere. And then finally, here's the sill again, and so it's just kind of like a ridge in the bottom. And I will leave my takeaways up here since I'm out of time. Thank you.
And be reminded that Veronica is a student, so if you could go ahead and use these QR codes to provide some feedback for her, that would be awesome. All right, so for our next talk, we'll have Caitlin Locke, who will be talking about the grounding of Venable in Antarctica.
Hi, everyone. I'm just going to check this first. Oh, let's see if I can do I'm going to keep doing this one. Okay. Hi, everyone. My name is Caitlin Locke, and I am a fourth-year PhD student at Lamont Doherty Earth Observatory. And the title of my talk today is The Novel Record of Grounding and Ungrounding of the Venable Ice Shelf Since 1906. And before I start, I'd first like to thank my co-authors, Kirsty, Tinto, Dave Porter, and Renata Constantino for their support of this work, and also NASA Operation Icebridge and the WAIS Organizing Committee for the early career support that helped bring me here today. So, a quick outline of my talk so you know where we're going. First, I'm going to start with my motivation, which is this ice shelf thickness record to 1973 that was published earlier this year. Following that, the Venable Ice Shelf bathymetry model I have been working on should be out soon, get excited. And then the current Venable Ice Shelf pinning points, and then a past pinning point beneath the Venable Ice Shelf that we believe we've identified. Following that, our method to extend the ice shelf thickness record below the Venable to 1906, and some conclusions. So here is Miles and Bingham earlier this year used satellite-derived surface expressions to measure ice shelf thickness change back to 1973 on the Venable Ice Shelf, as seen here. And they extended the record through the satellite era by proxy through measuring the change in the area of these pinning points. And pinning points, as you see here, are local subice shelf bathymetric highs where the ice shelf is attached to the ice base. And they're incredibly important because they provide buttressing to the upstream ice flow, which reduces ice discharge across the grounding line. So after I read this paper, I happen to be also working on the Venable Ice Shelf bathymetry model, when the Venable Ice Shelf is right here below the Antarctic Peninsula. And to create this bathymetry model, you see here is bed machine, and then here is our bathymetry model that should be out soon. And we used airborne gravity data from Operation Icebridge to invert for bathymetry. And we were able to show that there are deeper troughs that provide pathways for warm ocean water to access the grounding line, in addition to shallower regions at the ice shelf front here and here, in addition to in the western portion of the ice shelf right there, and the little one right there. And these shallow regions that we identified correspond to previously mapped pinning points, as seen here. But what about the western portion of the ice shelf? This bathymetric high is 520 meters high. Could this be a sub-ice shelf topographic high that is a former pinning point? So I went to Landsat imagery from 1973 to 2024 in combination with our model bathymetry to investigate if there is a past pinning point beneath the Venable Ice Shelf. And we believe there is. Yay! So here, showing a GIF of satellite imagery from 1973 to 2024, and once it starts again, you'll see that there are crevasses that appear to propagate off this bathymetric high, and after 1988, they march towards the ice shelf front, leaving the record in satellite imagery. And it reminded us, as I said, that Miles and Bingham paper, they looked at this pinning point that is in the eastern portion here that has fractures propagating off both sides, whereas for this one, they just appear to be on the left side. So we propose that there is a past pinning point beneath the Venable Ice Shelf and that it has been intermittently grounded since 1906 before finally ungrounding in 1988. And now that you've watched this GIF a bunch of times, let's walk through those slowly. So to derive this grounding history, we used a velocity rate derived from crevasse change between 1973 and 1988, and then backed that out. So here in this image, we don't know if it's showing, but here, between 1906 and 1953, we believe the ice shelf was grounded because there are crevasses that are a little hard to see, at least from this angle. Hopefully you see them. And then from 1953 to 1970, there is a crevasse-free period, which we interpret as being ungrounded. And then between 1970 and 1988, there's a crevasse packet that we believe was grounded, followed by, from 1988 to present, ungrounding and the slow march of these crevasses towards the ice shelf front, which you can see in 1997. And then in 2020, we see that 1988 crevasse that originated here for the final time. And then earlier this year, it's gone. And this little crevasse that I've identified is something that opened up later in the satellite imagery, which we're not sure about the mechanism. And so here is the Miles and Bingham figure that's so wonderful that shows how they identified these ice rises and pinning points. And we'd like to propose an additional mechanism. So you can have an ice rise, as seen here, with crevassing coming off of it. And then that ice rise can become diminished as the ice shelf thins. There's still crevassing happening. And then there is no ice rise. It's thinned. It's above the pinning point, but those crevasses are still seen in the satellite record, as shown here, and as we showed in my figure. And I didn't mention, this is our survey line that went right over the pinning point, so yay. And this paper from Miles and Bingham showed that there has been thinning beneath the westernmost current ice rise at least 50 years ago, and then along all 4 current ice rises at least 35 years ago. And here now we can extend that record to 1906 by saying that there was thickening about 118 years ago until 1906, or until 1953, and then there's thinning beneath this westernmost pinning point at least 71 years ago. And then beneath this, or above this pinning point, I guess I should say, there was thickening in the west here at the same time that Miles of Bingham was showing thinning here, which is interesting. And then thinning from 1908 onward along all of the ice rises. And so just some quick conclusions. We identified what we believe is a past pinning point beneath the Venable ice shelf, and we believe that we've shown you that it has been intermittently grounded since 1906, and then it finally ungrounded in 1988. And we hope we're demonstrating that there has been thinning and loss of ice shelf buttressing on the Venable ice shelf for about 70 years. And we've presented this new method to extend this ice shelf thickness record beyond the satellite era that we hope to apply to other ice shelves. And I want to just say thank you very much. It's really nice to be here. So.
We do have a minute if someone wants to ask any questions. While I'm changing these over. Also be reminded that Caitlin is a student, so if you can send in feedback, please do so. Yeah.
That was a great talk. Would you have any interest in historical images off this coast that might show those crevassing?
Yes, sorry.
So I did look at the aerial footage from Antarctica from the 60s, and unfortunately it doesn't go over, but if there's more that you know about, I would love to see it. Yeah.
There's just some ground.
Oh, yes. That's great. Yes, I would love that. Yeah. I'll come find you. Thank you.
All right, so next we're going to have Allison Chartrand, who's going to be taking us over to Thwaites Glacier to think about ice shelf basal channels.
Thank you. Okay, hi everybody. I'm Allison Chartrand. I am presenting today, and I'm grateful for the opportunity to present this work from the late stages of my PhD. I'm now a postdoc at the University of Maryland and NASA Goddard working on Greenland, so glad to be back in Antarctica for a bit. So this work was motivated by the fact that throughout my PhD, Ian Howard and I were really interested in what we could do with the reference elevation model of Antarctica data. So this is a series of digital surface models that are time-stamped from the entire continent, derived from stereophotogrammetry. And it was part of a larger project to see what we could use REMA to tell us about ice shelf change in general. And my part in this was what could it tell us about grounding line change. And as we were ramping up this project, a couple really cool papers came out about some Greenland ice tongues where they saw that grounding line retreat was faster where the ice shelves were channelized. So if you're unfamiliar, an ice shelf channel is essentially a deep groove at the base of the ice. It can be incised either by a topographic high in the bedrock before the ice shelf becomes ungrounded, or by enhanced melt. That shape gets advected out, and buoyancy causes a surface depression to form as the ice relaxes towards hydrostatic equilibrium. So yeah, these papers saw that ice shelf channels that were extending from subglacial channels really hypothesis driven. So we used the REMA strips, which are individual maps of X, Y, and elevation. They're about a few kilometers to tens of kilometers wide and tens to hundreds of kilometers long along the satellite paths. And we use these in a number of ways. So strips or the DSMs are a little tricky to work with, admittedly. You have to correct for tides, the geoid, dynamic ocean topography, and you have to register them in space vertically. So we used Cryosat 2, IceSat 2, and IceBridge data to do that. And with each individual strip, we then mapped a proxy for the grounding line, which we're calling the hydrostatic boundary. And we also mapped ice shelf channels from their surface depressions. And we also used the strips to create annual mosaics of the surface for each year. Combine all the strips from November to March of any given year to get a as continuous as we can surface. We gave them a nominal date of January 1st, and we used these to derive maps of thinning and basal melt rates on the ice shelf. And finally, we were curious what we could find out about subglacial drainage, so we just did a first order estimate of where we might expect to see subglacial water routing based on the hydraulic potential. And we did that with the static REMA mosaic. So just a little more detail about the hydrostatic boundary mapping method. We used the ice surface height and the bed topography from Bed Machine. The difference between those we called the grounding thickness. It's the thickness if all the ice were grounded. And we compared that to the thickness the ice would be if it were all floating. And where the difference between the grounding thickness and hydrostatic thickness was 0, we assumed that was where the hydrostatic boundary is. We use this as a proxy for the grounding line. So like I said, we used the individual strips to map surface depressions. As you can see, the results were very noisy and messy. So we filtered out everything that looked like a crevasse that was oriented orthogonal to flow. And from that, we identified 7 ice shelf channels that seemed to persist throughout time. They're marked by the green lines, and the dashed lines are where the surface depressions extended inland of the grounding line. And we also used these strips to map individual hydrostatic boundaries. Again, very messy. You can start to see some regions where we have retreat. The colors don't show up wonderfully. So hopefully this is a little better. We smoothed these hydrostatic boundary features and excuse me, combined them by year to get an annual hydrostatic boundary. All right, and so like the title of the talk suggests, the grounding line thinned and retreated fastest where ice shelf channels were present. The only places where we saw retreat in the absence of basal channels was here and between channels 3 and 4, and here kind of parallel to channel 7. And we distilled these into 3 major types of retreat that were associated with channels. So we have narrow cavity retreat along channel 3 and 5, wide cavity retreat along channel 1 and 4. And channel 1 also kind of switched to narrow cavity retreat toward the end of the study period, and then little to no retreat are along channel 6. And notably, all of these ice shelf channels, except for 4, were aligned with inferred subglacial drainage pathways. And interestingly, 6 is along the most intense subglacial drainage pathway, but saw the least retreat, but that might be a place to watch out for in the future. I think I'm talking a little faster than I have been in practice, so we can spend a little more time on this slide, which is exciting. So one really cool thing about the REMA data set is we can get time-evolving rates of change. So here we're zoomed in on the eastern portion of the shelf. On the grounded ice, we have the Eulerian thinning rate, so just how fast is the surface changing, because we're assuming the bed is static. And on the ice shelf, we have basal melt rates that we derived using the hydrostatic assumption. And what I want to point out is that we see a lot of retreat, like I said, along Channel 1, and it's preceded by these really intense zones of grounded ice thinning, and similarly over here in between the two channels. And we saw that across the board. I've honed in on this spot, but saw that across the board. And I also wanted to highlight this profile, which is the surface heights along the along Channel 1. 0 marks where the reference grounding line is, which we took to be the 2007-2009 International Polar Year grounding line derived from INSAR. And the vertical lines are the intersection of our hydrostatic boundaries that we derived with that channel. And so you can see a lot of retreat, but you can also see the ice shelf draft that we derived, and the cavities that are opening up are really shallow, like on the order of tens to hundreds of meters. And these aren't resolvable by a lot of the current coupled ice ocean models that we use to map and predict grounding line flux and ice sheet mass balance and its contribution to sea level rise. So if your interest is piqued by this talk, the paper just came out last week, and you can find it at that QR code, but I hope I've convinced you that we see the most retreat where channels are present, and excuse me, that REMA is really powerful for getting time-evolving melt and thinning rates for thwaites in its ice shelf. But an area of research I'm really interested in going forward is how reliable is that hydrostatic assumption. Some work has shown that the ice isn't actually freely floating, particularly around things like ice shelf channels. So I'm really interested in the spatial scales over which the ice is or is not freely floating and what the impact is on thinning and melt rates that we derive from surface data. So would love to chat about that more. Thanks.
We have time for a very quick question if someone wants. All right, well, we'll move on for now. Next, we're going to have Alex Robel, who's going to be talking about Antarctic grounding zones.
Great, all right. Well, thank you all for coming here to the Southeast. It's really exciting to finally have a WAIS here in a place where it's 85 degrees in November. I think the other exciting thing about that, and just sort of echoing what Mickey said this morning, is, you know, for those of you who are interested in how the things that we're talking about here impact vulnerable communities in coastal areas, where the greatest concentration of those in North America are here in the southeastern United States. You know, please find any of us who are sort of working on these problems here in the Southeast, and you know, I think we'd be happy to chat with you more about sort of the translation of glaciology to thinking about, you know, how communities are living with this change and trying to adapt to this change. So, moving back to polar areas, though, today I'm going to be talking about seawater intrusion, which is really a great follow-on from Allison's work. I'm Alex Robel, and I'm an associate professor at Georgia Tech. Okay, so here's a cartoon of what we've been talking about for this whole session, the grounding line. So it's the triple junction between the ice sheet, the ocean, and the solid earth. I can see my colors have been messed up, but what you would see here is a lighter blue color that is the subglacial gap between the bottom of the ice and the solid earth. And we are interested in this question of what happens at this interface between subglacial discharge and seawater. Why is this question important? So we posed this question 2 years ago in a paper in the cryosphere, and what we did to answer why is this seawater intrusion, potential seawater intrusion important, is we took a model, ISSM, and in a few benchmark simulations, we took sort of, this is the normal situation of how an ice sheet model simulates heat at the grounding line, which it assumes that under floating ice, under the ice shelf, you will have melt driven by the ocean, and then once you get to the grounding line and upstream of the grounding line, that melt drops to essentially 0 or order millimeters per year. So what if instead there was this distance over which this basal melt rate from the ocean dropped off, right? And I'm going to talk about in the back half of the talk, or after these 2 slides, whether this is occurring. But so we just imposed some hypothetical intrusion-induced melt over some distance, and then we ran some benchmark simulations. So if you're a modeler, this is the MISMIP plus ICE1R, if that doesn't mean anything to you. It's just a benchmark simulation of a marine ice sheet. And so what you're looking at here is basically the volume loss after 100 years under a variety of different simulations where we impose this additional distance upstream of the grounding line where ocean-driven basal melt was occurring. Right, so the black dot is basically what models do now, all right, assuming there's no melt upstream of the grounding line. And then the colored dots, the blue colored dots, are assuming that there's basal melt progressively further upstream of the grounding line. So the upshot of this is that if you have a few hundred meters of intrusion, it is equivalent to doubling the basal melt rate under the entire ice shelf. If you have a few kilometers of intrusion, it is equivalent, or it produces double the marine ice sheet sensitivity to ocean warming, right? And what I'm not and so if you do the same thing for a benchmark simulation for Thwaites, since we're at WAIS, we want to think about an actual real glacier, not just an idealized one on a computer. A few kilometers of basal melt upstream of the grounding line in a standard simulation of Thwaites over the next few centuries produces a few hundred years faster collapse of Thwaites just due to a few additional kilometers, right? And that's one mesh element in a typical large-scale ice sheet model, right? So what's going on just upstream of the grounding line, what's going on in this interesting fluid mechanical environment is really, really important, right? The other things that, for a 10-minute talk I'm not showing here, but there have been other studies which have shown that if you do this for all of Antarctica and you allow some melt upstream of the grounding line, it doubles the sea level contribution of Antarctica over the next 100 years. It might also help explain the sensitivity of Antarctica and why it seemingly collapsed during the Pliocene. So seawater intrusion is potentially important. Before I proceed, I also want to kind of sketch out my philosophical approach here. What I've just argued here is not that this means that seawater intrusion is happening, right? It is one potential explanation for some existing conundrums within the field. So in going forward with research on seawater intrusion, the way that I think about it is that seawater intrusion is a hypothesis, and as scientists, our goal is to falsify this hypothesis, and if the science that we do does not falsify this hypothesis, then it is our job to constrain this hypothesis further. So that's what I'm going to do moving forward. So because of the short talk, apologies, I'm going to hit on a few different projects really quickly. That same 2022 paper, what we did was we developed a 2-layer shallow water theory for what happens across a grounding line. And so this assumes no mixing between the ocean and the fresh subglacial discharge. But basically what we found, what the sort of prediction from this simple theory is, which sort of produces a single number, which is the intrusion length scale, is that if the bed is retrograde, if the subglacial gap and water layer is thick, so order centimeters or thicker, and if the discharge rate from subglacial water is relatively low, so order centimeters per second or less, all of which are conditions that we expect occur in large parts of Antarctica, then we expect that, we predict that intrusion would occur over length scales of hundreds of meters to several kilometers, right? So that's the prediction from a simple theory, right? There's been some other really exciting work that just came out in Nature Geoscience by Alex Bradley and Ian Hewitt that shows that actually the intrusion would go even further if the theory accounted for how subglacial channels widen as the intrusion moves in, widens them, which then produces a positive feedback that causes them to paper. I suggest you go look at it. My student, Madeline Mamer, has been working on sort of the next step of this, right? So that was a simple theory using a lot of assumptions. What Madeline's been doing, and this is in a preprint that is up on the cryosphere, is currently in revision. So I suggest you go check this out if you're interested in all the gory fluid mechanics details, is she takes a CFD solver that resolves basically turbulent mixing down to a resolution of about 1 millimeter and simulates one of these sort of subglacial gaps and the transition to the ocean basin. And basically what she finds is that including turbulent mixing actually only has a minor effect on the mixing between subglacial discharge and seawater. That is to say, when we account for turbulent mixing, which was not included in the simple theory, it doesn't really prevent intrusion, which was a big surprise to us. But that's largely because there's not that much turbulent mixing if the flow rates of the subglacial discharge are low, because the Reynolds numbers are very low. The other thing that she found, though, is that something that's not accounted for in the theories is that when you start to melt from the bottom of the ice, this basically stratifies the water column underneath the ice, and this depresses melting. So you don't have, as I show on this slide, you don't have the melt rates that you would predict from a 3-equation parameterization, because that parameterization assumes that you have a fully turbulent boundary layer, which is not the case here. But instead, you have melt rates that would be predicted more by a diffusive or double diffusive parameterization of basal melt. So if we're going to put all these things into models, right, we need to start thinking about how we can have an ocean-driven model of basal melt that can transition from a 3-equation parameterization to double diffusive convection within sort of the same model. That's not something that currently exists. The other exciting thing that I want to talk about is sort of how do we take these, again, simple theories and bring them into reality. So this is, I don't know if the animation's playing, but this is, we're in the midst of a 4-year NSF project. This is in collaboration with an experimental fluid mechanic at Georgia Tech, Chris Lai, and his student, Mohammed Mustafa. So we built an ice shelf / vertical ice front in the lab, and we can create plumes of arbitrary geometry or velocity over several meters scale. And the exciting thing is that they can then measure the temperature, salinity, and velocity simultaneously in the boundary region of this ice-ocean interface. So we're basically getting the measurements that are so hard to get into the field, but we're doing them in the lab where we have all this wonderful equipment. And okay, you're not seeing any of this because the colors are all washed out. But this is an example of what you can do. So this is a measurement of temperature underneath a block of ice melting in ambient melting of water, of the ice. And so they are measuring the temperature, salinity, and velocity here at 1/10 of a millimeter resolution. So that's really going to help us to build sort of the next generation of basal melt parameterizations. All right, I see that I am being kicked off, so I am going to jump to open questions. I always prepare way too much for my WAIS talk. But in thinking about seawater intrusions, this sort of like exciting new question and problem that produces this exciting science, I'm sort of interested, and I think that there could be lots of community effort around this question of sort of the interactions between subglacial hydrology and ocean dynamics, and how do we get subglacial hydrology models and ocean models to talk to each other at a high resolution. Thinking about observational tools. I skipped my observation slide, but there have been some really great observational papers suggesting that seawater intrusion is happening at a lot of grounding lines in both Greenland and Antarctica, and I think we're going to hear tomorrow from Peter Washam about a really exciting ice fin observation that might be showing direct confirmation of seawater intrusion, and how do we then close the gap between these contemporary models, which seem to indicate that marine ice sheets are not that sensitive to ocean warming, and past high sea level high stands. Is seawater intrusion sort of the solution to that problem? And so since I'm well over time now, I'm happy to answer your questions during the panel, which I guess is about to start. Thank you very much.
All right, well, I think we'll just move on straight to the panel. I think we'll have plenty of time for more discussion, and thanks to everybody for those great talks. It was a really broad spectrum of discussions about the grounding line. We went all the way from, sort of airborne geophysics to remote sensing to direct observations and to some theoretical work to motivate a lot more observational campaigns. And right now it's 11:36, and so we're going to go until noon. And so does anybody out in the audience want to start us off with a discussion?
Awesome, super interesting session. I have a question for Alex and maybe Allison as well. Do you think there are any subglacial or grounding line geological conditions that lend themselves most towards seawater intrusion and would make that intrusion have the biggest impact on ice sheet retreat?
So you were asking, are there geological indicators?
Or do the geological conditions modulate the seawater intrusion and its impact on the ice?
Yeah, so one prediction that we made in that 2022 paper was that, so oftentimes you hear the word seawater intrusion in the context of aquifers, right? Here in Florida, very, very relevant. And what we found is that subglacial till is not hydraulically permeable enough to really expect to have seawater intrusion more than a few meters past the grounding line. Now, there's other things that could be going on, but all of our predictions of seawater intrusion really have to do with a situation where you have some sort of hydrological system at the interface between the ice and whatever the substrate is below. And that still could be sediment, right? It could be that you have saturated sediment that then produces a situation where you still have like canals or channels or things like that above that. Yeah, it probably wouldn't be happening within the sediment itself. So I would say that would be the one sort of geological prediction that we make.
Thank you.
Just to follow up on that, if in areas where we think there was Holocene retreat and readvance of grounding lines, you might expect that there could have been salt saturation of sediments such that even though right now salt isn't intruding that far, there's hundreds of maybe kilometers of sediment whose freezing point is lowered because of salt, and so the salt might already be there. I wonder if you had thought about how that could play a role.
Yeah, that has to do with something that another paper of ours that I did talk about here in this talk, but about exfiltration in the subglacial aquifer. And yes, I think if we were able to measure basically the salinity, and there's been some really nice work done with like electromagnetics. So Chloe Gustafson had a great paper on this a few years ago, measuring basically the salinity of subglacial groundwater, which at how far that was upstream of the grounding line, that was probably, in their paper they suggested that it was indicative of a, hypersaline water, relict fossil groundwater that was then being released into the subglacial lake. But if you had such measurements, closer to the grounding line, or even of pore waters in the subglacial cavity, then that might give you some indication for, some history having to do with that. And so I think Ellie Miller's poster will have some things to say related to these sort of paleo exfiltration rates.
Hey, I have a question for Allison. So in your figure of the butterfly of Thwaites, there's these stripes of high melt rates that were aligned perpendicular to flow. They look like crevasses. And from what we saw with the field data, it seemed like most of the strongest flow was like along coastline across ice flow. And therefore we were seeing that being the primary ocean forcing direction. And then the crevasses having the highest melt rates. But what happens when you have that and then an ice shelf channel intersecting that? So I don't know, and I was just curious to hear sort of, because I haven't read your paper yet, what you gleaned from that sort of information in your data.
Yeah, that's a really great question, so thank you. And I'm really interested to hear that you think that those like stripes of melt or freeze-on might be real. I kind of assumed that they were just a relic of the flow adjustments that we did for the Lagrangian melt rate calculations. But yeah, that's really interesting. I don't know the answer. This would be a great thing to look into more. We did identify a lot of like surface depressions in that area, likely due to crevasses. I didn't do a whole lot of like verification of what those features were because I was more interested in what was happening along flow. So yeah, I don't know the answer,
It was
but very
not a
interested
very
in figuring it out.
well-developed question, more like a rambling thought, but yeah, it's fair enough. It could they could also just be relics from crevasses popping, but yeah, interesting to think about at least.
So Allison, I was going to ask you this after your talk, but then I realized Alex might answer it for me, and he sort of did, but I'm going to rephrase it, I guess, which is you see this connection, this correlation between where you have channels and where you have grounding line retreat and high melt rates and all of that, but like what is the process actually driving all of this? Is it the subglacial water coming out? Is it perhaps intrusion because we have this nice big funnel going in? And the reframe after Alex's question, and I think you hit on something really important, which is this transition between our melt rate parameterizations. And you were talking about it spatially, but you can imagine as the grounding line is evolving, you also have it temporally. And how do we set these thresholds to change it? I don't know, I'm just really interested in like, can we start to distinguish actual base melt processes to that granularity to be able to send it off to a modeler?
Yeah, great question. I think we're getting to that point for sure. The work I presented, we didn't really go into like the oceanographic processes, the circulation processes that might be causing it. It did seem that because of the subglacial hydrology that we estimated, that all of the channels, except for one, were probably subglacially sourced, so that initial incision was probably caused just by the shape of the channel coming out from under the grounded ice, and then being enhanced by the ocean melting that we know is strong at the Thwaites grounding line. So that's the hypothesis. Would be really interested to get more granular than that. And I was thinking a lot about this during Alex's talk, the influence of, and actually from Mickey's question too, the influence of the bedrock topography on melt rate processes. It seems like seawater intrusions might happen more where there's a flatter bed, or doesn't it matter?
More on a flatter bed than they would on a retrograde bed.
Yeah, and what about a retrograde bed?
Even more so, yeah.
Okay, yeah, and Thwaites has a famously retrograde bed, so yeah, open question, would be happy to chat more. Do you want to?
I guess from the modeling perspective, what I would say is that I think we're probably on the verge of a rethink of how we connect ocean models to ice sheet models. Because there's been so much effort on coupling over the last 5 years among different modeling groups, and there are many different efforts to sort of rethink the parameterizations that we've been using for a long time, but also having flexibility in terms of like what kind of parameterization you're using. I think what's complicated here is that the processes that I'm talking about are all occurring over a horizontal length scale of like order a kilometer, right? And that's the order of one grid element in an ice sheet model. And so how we get those into ice sheet models at their modeling or something like that, those are questions that we're thinking about now.
Questions that might be answered by some rings.
Well, yes, indeed. I was excited about that scale. I also, since I've got the microphone, even though there's a line of questions, I wanted to check when you said that the channels were subglacially formed. Is that from the grounded topography, which made me think of Veronica, and that you had seen the base of the ice tracking to what it had been grounded on previously? Or is it from onshore hydrology?
Onshore. Yeah, a little bit of both. So we did the hydraulic potential. We did a hydraulic potential calculation. So I think I would have to look at the math, but it seemed like the water was being routed along subglacial troughs due to the overlying hydrostatic pressure. I think I'm fuzzy with equations.
Let's go up front and then we'll go to the back. Oh,
Sorry. Yeah, I guess my question is for everyone, but it's motivated by Alex's talk. So I'm intrigued by the sensitivity of the mass loss to increase of the seawater intrusion land scale. I think this is really important. And I was wondering if any of you have insights on the driving mechanism. You know, is it related to the loss of buttressing due to the detachment of ice from their bed, like a little bit like Hegelein's, what Hegelein showed, the loss of buttressing, or is it something else that set that sensitivity?
Yeah, so there have been a number of modeling papers that have actually showed the same thing, just sort of couching it in a different way. Particularly, there have been, Helen Sarusi had a great paper, and she was on this paper as well, looking at this more the question of like, how do you deal with the transition from grounded to floating ice in a model, right? Both in terms of friction and in terms of basal melt. And basically found the same thing. So when we did those simulations, we kind of knew what the outcome would be, but we just did them all at 100-meter resolution to ensure that it wasn't resolution dependent. But the answer is basically you are melting in the place where the most buttressing is happening, right? It sounds weird to say that the friction at the grounding line, or like the grounding line, is where buttressing is occurring, because we sort of think of buttressing as being due to friction that occurs downstream of the grounding line. But ultimately, buttressing, or longitudinal stresses, which is what sort of buttressing is related to, just has to do with how much integrated basal and lateral stress you have, right? And if you are suddenly unpinning or causing flotation at the place where the grounding line is, then it's going to have the biggest impact on subsequent retreat. And so I think, yeah, it makes sense. And I don't think it's a surprise to anyone, given all the other talks in this session, that like saying knowing what's going on at the grounding line is really, really important to getting simulations right. But I think it's sort of a reiteration and also a hypothesis pointing towards a physical process that could be driving this.
Thanks for great talks. I have two questions, one for Allison and one for Alex and Allison, I think. And the first one for Allison, I think it's fairly simple. The channels you identified connect to static hydropotential pathways for drainage, which connect to the subglacial lake system upstream on Thwaites. And there have been 2 drainage cycles during your observational time period. Do you see evidence of enhanced retreat in the vicinity of these channels that would be temporally consistent with the lake drainages?
I love that question. And that is one thing that we wanted to look into and then ran out of time because I was graduating. There are some channels that experience like really rapid retreat in some years, and I would really be interested to see if they line up with the drainage patterns. And in some cases, those really rapid retreats were also associated with velocity changes in either direction. So I didn't really find a pattern, which I'm assuming could also be caused by some of that subglacial lake drainage. So yeah, one thing that we didn't quite get around to looking into, but is very probable.
Yeah, and the drainage cycles were quite different, and so how the temporal variability, if there is a link, manifests, I wouldn't necessarily expect to be the same if it's there at all. My second question is maybe more conceptual, but if seawater intrusion is occurring, Alex, you just mentioned some geometric factors that might affect it. What would you expect the spatial variability in the length scales of the seawater intrusion to be, and how might that affect the retreat rates? Because I think if you were to impose this on an ice sheet model, you'd want to incorporate that somehow to get an accurate set of retreat rates. I'm interested in what factors are important there, both geometrically and also in terms potentially of circulation. So you see enhanced intrusion near subglacial channels, for example.
Yeah, so I think, I mean, ultimately, like what the theory predicts is that you'll have more intrusion in places where the subglacial gap is thicker, right? So if you have a channel there, then you're more likely to get intrusion, and a lot of the observational work that I skipped over, but that has come out in Greenland and Antarctica has shown, you know, exactly what Allison talked about, which is that in places where we know there are channels, there's intrusion occurring, or there is evidence for indirect evidence that there is intrusion occurring. One thing that I had on my slide that I skipped is the famous CAM channel, which again, we're gonna hear more about, right? There's radar, you know, there is published radar data that channel is 200 meters tall, right? That is the cavity upstream of the grounding line, right? And again, I'm gonna pose it as a hypothesis, but it would be, I think, very, very hard to explain why there is a 200-meter high channel upstream of the grounding line unless ocean heat is getting upstream of the grounding line. And I think there is now going to be direct evidence to that effect. So I think, yes, so getting to your point, how do you get this into models? Ultimately, this comes down to the sort of problem that we've now had for about a decade, which is the mismatch of scales between subglacial where subglacial hydrology acts and ice sheet models, right? And primarily subglacial hydrology models have been used to get at the sliding question, right, in models. And so you can sort of diffuse basically their effect because there's a radius of effective pressure change from a channel that can be, you know, sort of represented in some way in a coarse ice sheet model. But when it comes to the melt, right, we're seeing evidence that there are these regions of like extremely concentrated basal melt associated with channels. And so how we handle that in models that are inherently like 1 or 2 kilometers resolution is, I think, yeah, an open question.
So listening to the talks, when I was thinking about processes like channels or meltwater intrusion over hundreds of meters, it seemed to me that the way we would want to observationally constrain this with radar is like hardcore repeats, sort of 1 or 2 kilometer upstream, maybe sub-tidal cycles, and really see the water intrusion modulation or really see exactly where water is hitting the grounding line. This seems structurally opposite of big old rings around the whole ice sheet. So how should we spend our limited airborne resources?
I'd say complementary. If you're gonna fly back and forth for a few days to watch this happen, we've designed a line that you could fly along that'll help everybody. So yeah, I think it's you know.
So I guess the question is, my imagination with intrusion is you do it along flow.
Oh, well, you got to turn corners.
Okay, there you go.
Yeah, since you're going to have a gravimeter on board as well, so you'll be heading for the offshore section. Thank you. Yeah, you can. One of the things that we want to do is to make sure that where there are good process-based questions getting flown, then those can build into the cohesive picture all around the continent. So you don't have to have one person in a plane doing a single circle, but fly somewhere that's useful and then send somebody else somewhere that looks a bit the same on the other side to see what it's doing.
So I should have known that as Dusty student, I'd be asking a follow-up question to the person standing in front of me. But yeah, so you know, Kirsty, you're talking about the ring surveys, and that's obviously going to get us a bunch of new data around this grounding zone area. All of you were talking about subglacial processes that are occurring at scales where maybe directly observing the geometry of what you're talking about, or even the radiometry of it, is difficult, unless you have ice fin in situ, of course, which is, you know, maybe the ideal situation. But what are those spatial or temporal patterns where the differences might be something we could observe, that we could predict what the pattern might look like for any of the processes that you're interested in?
That's a great question. I've been thinking a lot about this. It's really interesting looking at the observational data of these subglacial processes, seawater intrusions especially, because a lot of the observations are over days, right? That's where we see these intrusions filling and draining, excuse me. But the spatial resolution, especially of like the interferometric radar, doesn't necessarily give you the detail of like where the surface depressions are, but you can get that from things like ISAT-2 and REMA, but those don't have the temporal resolution that you need to observe these events. So there's the problem. Any solutions?
I think I'm going to present another problem, and this is from 15 years of aggravation. I think Veronica's image of basically the cavity narrowing to the point you can't fit ice fin anymore really represents something I'm struggling with, which I think Alex seemed to struggle with in a much grander scale, but like defining this grounding line, right? If you have a 200-meter ocean cavity upstream of the grounding line's wrong, in my opinion, as an observational guy. But for a model that's very different, right? The modeler comes at it with a very different perspective. Like, what is a grounding zone in our world anymore? And if it truly is where ice touches ocean, right? That's a salinity change in the water that's underneath. How do we deal with that? Are we going in and actually sampling these waters to see where it's brackish, see where it finally turns into seawater? Like, I struggle with this a lot. So as people looking at grounding zones and grounding zones changing, I'd be very interested in your perspective.
I think that's a great question, and it is something I thought about after seeing your talk, Alex. I think that from an oceanography perspective, I'm inclined to think of the grounding line as being the point where you don't have any more ocean, even if it's like a very narrow area. But I understand that that would be hard to put into models, and given how challenging that is, I wonder if there's a way to define it tidally, of a point where you could get farther seawater intrusions tidally, but I guess a point where the ocean is always there no matter what could be a reasonable definition. But yeah, I think that if there is a measurable amount of seawater underneath the ice, then maybe that's not the grounding line at that point, is my inclination.
Yeah, I like that. And I think that we're on the brink of having more than one grounding line, because thinking about Allison and, where is it free floating? There's a grounding line that's way offshore as well. And we're going to have a bunch of different ones for different purposes, a little bit like the bunch of different mohos that we've got going on. And yeah.
But does that scare you, Alex, as an author up there?
The grounding line is a modeling convenience. That is, I will just say that way to decide when to stop our ice sheet model and when to start the ocean model, right? Or when to, in the case of like the intrusion problem, when to stop the subglacial hydrology model and when to start the ocean model. So it is a complete convenience born out of the fact that we need to have coupling schemes and these sorts of things, right? There have now been like several decades of papers asking the question, what is the grounding line exactly, right? And calling them estuaries, and which is exactly where we take all this theory from, is estuary literature. And so I think, I mean, maybe this is a bit too certain, but I think it is fair to say that the grounding line, there is no one grounding line. And we need to now reflect that in how we write down the equations that our models solve, right? So for example, right, that might be, part of the problem with that is that it was identified, right, 15 years ago that you need to have lots of resolution in your ice sheet model around the grounding line in order to make an accurate simulation, right? And now we've spent a lot of years getting all of our ice sheet models sort of on board with this. And now if we're saying, well, we're not going to be able to track the grounding line anymore because there isn't a grounding line, then we need to sort of change how our ice sheet models do that. I think we're probably at the point where we can have high enough resolution in our ice sheet models if we're talking about relatively short timescale simulations that, that's possible. But the hard part is with the ocean and the subglacial hydrology models, right? At the end of the day, they are solving the fluid mechanics problem, but we make totally different assumptions in the two different kinds of models. So yes, in the ideal future, there will be one integrated model and you can, resolve vertical resolution of 1 centimeter or something like that, but that's a very far future away. So developing the theory, doing the experiments, having the observations to support how we bring this understanding that we have of this transition into our models in a way that works with the models that exist now, that's very important for us to do as modelers.
One last question, and then we'll do Locke. All right, because we're running a little behind.
Thank you. I thought there was no grounding line anymore. It's all grounding zone, right? I have a question for Caitlin. So these pinning points are popping up, right, and here and there, and people using Landsat. Has there ever been a comprehensive study using all the Landsat data that are available over the last 50 years we have the computational powers now to actually look at all these pinning points that may exist, that may affect models, affect ice shelf dynamics, etc.? I'm just curious.
So the one that I found is that Miles and Bingham paper from just earlier this year that was the first one I saw, a comprehensive study of all of the Landsat imagery, only looking at those topographic ice rises and how they changed over time. Prior to that, I hadn't, so we're hoping to maybe use what we discovered to extend that and find more that can be used.
All right, yeah, thanks.
Okay, well, let's thank all of our speakers again, and thanks for a really great discussion. And we'll be back here at 1 o'clock. Thanks, everybody. And thanks to the speakers, again, for staying on time. That was really great.